Hello and welcome to the radio room. I'm going to do a little bit different type of video tonight than normal. Not really going to be working on anything, but I do want to go over a couple of things concerning multimeters, specifically in measuring voltage, and the fact that not all voltmeters are created equal. Um, Specifically, I want to talk about loading of the circuit. Each voltmeter, depending on what kind it is. Now this is a digital multimeter. Right up here, you can see it up in the in the inset there. This is a vacuum tube voltmeter, and each one of these has a different input impedance when you're measuring, different input resistance. Um, I kind of wish I had an old manual type here, an older one that would definitely show you the drastic changes between the two. But basically, when a voltmeter is measuring voltage, it's measuring current, really. Um, so there's a series resistance in the voltmeter itself that that voltage is going across, which of course, if you know the resistance that the voltage is being put across, and you can measure the current, then you can determine the voltage. It's just simple Ohm's law. So anytime you have a voltmeter measuring voltage, it's actually running through a resistance that the voltmeter knows, and it's all calibrated off of that volts, that volts that, or sorry, ohms that it's running through. Digital multimeters and vacuum tube voltmeters generally have a set resistance, no matter what range you're in. I can change the range here, and it's still going to have the same input impedance. Same thing with the vacuum tube voltmeter. Old analog types normally were volts per ohm, or ohms per volt. I'm sorry. So it depended on which range you were in. So say you had a 10,000 ohms per volt was the standard for the voltmeter. You would multiply that by the top, what range you're in. So 10,000, right now I'm in the 20 volts. So if this was an analog one, it'd be 20 times 10,000, or 200,000 ohms that would be in series that it's measuring with. And that can come in really important depending on what circuit you're measuring. If it's a very low impedance circuit, then a low impedance on the voltmeter isn't going to make as much difference. However, if it's a high impedance circuit, that lower resistance that's now introduced to that circuit is going to change the way that circuit's working. You now have a lot lower impedance through that circuit, which is going to change your volts readings. So first off, I wanted to go and just kind of take a look at what is the ohms reading for these two voltmeters. So I got my VTVM. Right now I got it on ohms reading, and I'm going to go ahead and turn this up to about the times 1 meg ohm range. Well, let's start a little lower here. Let's start at the resistance times 10K. And I'm going to measure the resistance, internal impedance of this voltmeter. So I've already got my leads hooked up. This one's going to this one. So I need to have some test leads. This is my leads going to my VTVM over here. So since I'm going to hook this up, I'm going to go ahead and hook this up to this. And you'll notice two things here. First off, we have a voltage here. That's merely reading the voltage that's coming out of the VTVM that is going through this to measure the resistance. But if you'll notice, and let me go ahead and go to that that reading, and I'll just I'm going to undo the clips here. So we have a little bit of a change here. Didn't move much. It's still pretty high, close to the infinite. On VTVMs and some of these, a lot of these meters, full needle deflection is infinite. It's kind of a little bit backwards. You actually calibrate it at infinite with the leads undone. So that's pretty close to infinite. So let's step this up and see if we can get some better resolution. So this is going to go up to 100K. So I take my reading and I measure it times 100K. And we got a little over, well, let's go to another range. So I'm going to go to the 1 meg. First off, let me make sure that my meter is calibrated in this range. And it looks like it's pretty close. This is so high that even me just touching the end of the probe lead, since we're at such a high impedance reading. So I am going to make sure this is set right on infinite in that range. Okay. So let's find out. I'm in the 20 volt range, which isn't going to make too much difference. That needle swing you can see right there is just me literally grabbing the lead to the alligator clip on the end of the lead. Okay, so according to that, it's a little over 2 mega ohms. I'm switching through the ranges here. As you can see, it stays constant no matter which one I'm in. And that is the 1 times 1 meg ohm range. So it looks like we got about 2.25 meg ohms. Have that unhooked now. Now, my DMM here only goes up to about 2 mega ohms. So let's see if we can do that on the, I'm going to go to DC volts on the VTVM. And I'm just going to zero it out for a good measure. It is on 0 volts. And now I'm going to do the same thing to it, but I'm going to use this one to measure it. So I'm going to go to my highest reading here. And I'm going to do the same thing. As you can see, we do have voltage being read, pretty low. But you can also see that we have, it's too high for this. So this isn't going to work. The impedance of the VTVM is much higher than 2 mega ohms. So we're going to have to find a different meter to measure this with. So if you give me just a minute, I'm going to do a little bit of a camera change, and we're going to take a look at another voltmeter. It's all solid state, it's not vacuum tube, but it is a little higher quality than this one right here. And it will show a little better resolution and higher resistance readings as well. So let me go ahead and get that done real quick, and we'll be right back and take a look at what the internal resistance is of the VTVM. Alright, and we are back. I got you looking at another meter that has a higher resistance value than my little handheld DMM. And I'm going to hook it up to the VTVM, just like we did the other ones. and we will measure the input resistance of the VTVM. So let me go ahead and hook that up. There is one thing I'm going to show you here in just a moment, where we actually had an inaccurate reading when we were measuring the smaller VTVM. Well, I'll just go ahead and show it to you real quick. It actually had an erroneous reading for this one, and that is because VTVMs, a lot of times you have separate probes. This one actually has a combination probe, but you have a separate probe for DC and then one for AC and ohms measurements. The difference is on DC it adds an extra 1 mega ohm inside the probe, and I had it in DC when we were measuring the internal resistance of this one. I needed to have it over into the other position. If you can see, it just kind of rotates around here, and it takes that resistor in and out of line. So this is really where I needed to have it on ohms. So we actually had an inaccurate reading on that. But what I'm going to do is I'm going to go ahead and put it into DC, because I want to know what the input impedance of this VTVM is in the DC reading, because a lot of times when you're measuring something in a circuit, it may be a DC circuit. So I've already got the negative sides hooked up. I just need to hook the positive sides up, and let me go ahead and go to the bigger screen here so you guys can see, and we will hook it up. And this is in the DC. So if you can look at that, you can see that we're just over about 11 ohms. I have this set on the times 10 mega ohm range. So we take the one here, right there, and you can see that we're just above that. Now, just to show you that 1 mega ohm resistor is in line, I'm going to switch this over to the AC ohms reading, and you'll see it drop to just about right about the 1, which in this case is times 10, so it's 10 mega ohms is the input resistance for the DC voltmeter, or the voltmeter on this VTVM. But this is where we'd normally be reading it for DC volts, and that's got the 1 mega ohm resistor back in line with it. So let me go ahead and keep that right there on that one, and we're going to read the digital one again real quick. Got too many test leads out here. I'm going to go ahead and put these on here. We're dealing with such high resistances here that I don't want my body to be part of the reading. Just to give you an example. So these are the two test leads going to that. If you look at the meter there, just me touching it, see how much of a drop it makes just on that 10 mega ohm range? I mean, even if I'm just touching one of them. So I want to put these on here because I want to clip them to the leads here. And you'll see it's not going to matter where I'm at on that. So I go ahead and clip it there. I clip it there. Whoops. And I clip it there, and it drops way down. So let's go ahead and drop our reading here. Now I'm in the times 1 mega ohm. So I take my reading on the screen, which is just about 1. Multiply it times 1, we get 1 mega ohm. When we got the 2 earlier on the VTVM, I had it in the DC reading instead of the AC and ohms reading line. So it had an extra 1 mega ohm in line with it. That's why we got the 2 mega ohms. So you can see there's 10 times more impedance on these other 2 meters. And just to give you an idea, this one right here that we're looking at right here actually has a 10 mega ohm input as well. I've measured that in the past, so I'm just going to go ahead and let you know that. So you're probably asking, well, what in the world does that make a difference? Well, we're going to look at something here in just a moment, and we're going to see how this can make a difference. So let me go ahead and unhook these. I'm going to get this out of the way for a moment. And I'm going to get some stuff set up here. And we're going to look at a circuit, a schematic. We're also going to do a little bit of the math on it. And we're going to see what a difference 1 megohm can make versus a 10 megohm or even an 11 megohm resistance. So let me pause. Let me get things set up here. We'll get the dry erase up here, and we'll take a look at this and do a little bit of math. So hold on right there. Okay, so I've got the dry erase board set up here, and we're going to take a look at this. Now I got a schematic on the board here. We do have a power source over here. It's going to be DC, and we're going to just call that being 10 volts. Now, if you look in the blue, this is the circuit that we're wanting to make a voltage reading of between this point and this point. Say we're doing an alignment on a radio, or we have some sort of electronic device, and we've looked in the schematic or the service manual, and it's told us to test voltage between these 2 points. So let's just call this the negative side. Probably not right on the battery, but and this is our test point. Say that's test point 1 or something. So the service manual gives us a specification that there should be a certain voltage at this point. And we're actually going to figure out what that voltage is supposed to be according to this circuit. So the blue is the circuit under test. Let's just call it that. The red over here is going to be our voltmeter hooked up to it, which in this case I have 1 megohm right there because we're going to do it as if we were testing it with this one. But first off, let's find out what the voltage needs to be just sitting there by itself operating. So we're going to ignore this portion of it right now. We don't have anything hooked up to it right now, because as you can see, once we hook a voltmeter up to the circuit as those test points, it becomes part of the circuit. And that's where this impedance really comes in very importantly. Over here in the corner, you'll notice I do have some equations right here, and this is just 2 variations of the same. It's Ohm's law. Voltage, or E, equals IR, which is voltage equals current times resistance. This is the more specific way. Sometimes you'll see as V equals IR, but I always stands for current, E stands for voltage. So we need to find out what voltage should we have right here. Well, the first thing we got to do is we got some voltages and we got some resistances. Now I got 1.02 megohms right here. The reason for that is I've actually put a breadboard together of this circuit, and the resistors that I had, I wanted to come out close to 1 megohm right here, just to show you, because this would be a higher impedance, not a very, very high impedance, but a higher impedance circuit right here. And the resistors I had, the combination that I had to put together, I got 1.02 megohms right there. So that's why we kind of have a funny number right there. We do have a 100k ohm. I went ahead and wrote it out as 100,000 ohms, but it's 100k ohms. So we have resistance and we have voltage in this equation. We're trying to find out what the voltage drop is across this resistor. These two are in series. Since they're in series, we can just add these two together. So that's going to give us 1,100,000 right there. Actually 112 now. Or 20. Oh, sorry. I actually messed that up. Let me find my eraser and fix that, because I just about had that value wrong. We'll just do this straight out so we can do all the steps. I don't want to skip too much here. So we've got 1,020,000 ohms. We're going to add 100,000 ohms to it because these two resistors are in series. So we're going to find the total resistance in this circuit. I had it right to begin with. So that's ohms. I'm keeping it in ohms because it's a lot easier to do the math if you're in the base unit. So we have E equals IR. In order to find all the information we can here, let's find the current on this. So we're going to have 10 volts. Volts right there. We're looking for current. So I've reconfigured this to be volts over resistance, gives us our current. So 10 volts over 1,120,000 ohms. And that's going to give us our current. So I'm just going to use my phone as the calculator here. Well, let's see which way this is going to show up better. Perhaps like that. So 10 divided by 1,120,000 equals 0.00089, and I'm going to call it 3. So we have, move it to here, and then move 3 over. We got 89.3 microamps. So that tells us what this circuit, the current that's running through that circuit. Now we just need to find out what's the voltage drop across here. And there's two ways we can do this. We can either use our Ohm's law and find out here and then just subtract from 10, because the total voltage that's dropping across these two resistors has to equal 10. That's Kirchhoff's law. By the time you get all your voltage drops, you have to have used all your voltage, basically. Or we can just do it across this one. So I'm going to take this number, which we just got, and just double check and make sure I'm not missing anything here. I'm going to take this number and I'm going to multiply it by, we got current times our resistance, which is times 1.02 mega ohms. So take that, multiply it by 1.02 mega ohms. Gives me a very weird reading. So I must have missed a 0 or something here. I'm going to refigure this again. I got something in the wrong spot. We took our ohms, we added them together. So I might have just hit something wrong here. So 10 divided by 1,120. I did miss a 0. There's another 0 here. That makes more sense. I was thinking that current seemed a little high. Besides, the voltage I got was more than we had to begin with. So that's 8.93 microamps. Sorry about that. I must have I hit something wrong or copied it down wrong. So now we're going to multiply that times this resistance. So voltage, we want the voltage drop across this resistor, is going to be the current, which is right there, times the 1,020,000. It's still giving me a weird, oh, nope. Man, you get one too many zeros in here, it doesn't work. So it's 9.1 volts. 9.1 volts. That's what we need. That's what is supposed to be dropping across here. So if we were looking at our service manual and it said to read across here, it would tell us that we need 9.1 volts. Now, if you're looking at a service manual, most of the time it's going to tell you that you want to use a voltmeter with a certain input resistance or a certain volts per ohm, because that's the way it was checked when it was originally manufactured. So obviously we don't have a service manual for my whiteboard, so we're just going to assume that it's 9.1 volts right there is what they're reading. So it's going to, let's say it's going to be right around 9 volts, pretty much right at 9.05, 9.1 volts is what we're probably looking at right there. So let's look at this from the vantage point of if we use a 1 mega ohm input resistance voltmeter. So now our circuit has gone from being just a simple series circuit to a series parallel circuit. You see that? So now we need to find out what the total amperage is. Now I'm just going to write this down one time for you. Our original circuit had 0.0000893 amps, or 8.93 microamps. That's our original one. Now we've got to determine what's the total current through the whole circuit right now. In order to find this out, and you wouldn't have to do this if you were literally doing the test. I want to show you the difference between 1 mega ohm and 11 mega ohm. So now that this is a series parallel, what we really need to do in order to find the total current through the circuit is to combine these two. Let's just, as far as the circuit is concerned, these two are in series with this one, even though they're parallel to each other. So if they're parallel to each other and we only have two of them, we can do the R1 times R2 over R1 plus R2 equation to get our resistance total. Okay? So we're going to take 1,020,000 ohms, and we're going to multiply that by, I'm running out of room here, 1 mega ohm, or 1 million ohms. So let's do that. Okay, so it gives us a very big number right there. So we got 1, 0, 2, 0, 1, 2, 3, 1, 2, 3, 1, 2, 3, lots of zeros there. Now, we take R1, let's just call this R1, so you guys are all right with me. We got to add this and add this one together, and we're going to divide this number by that. So it's going to be divided by, this one's pretty easy math, it's just 2,020,123 equals. That's going to be our effective resistance total in this circuit between these two parallel resistors. So 504,950, and I'm going to call it 0.5 ohms, or about 505 kiloohms, roughly. So in order to find our total current through the circuit, we take the effective combined resistance of these two parallel ones, add it to that, and we're going to have our total resistance in the circuit. So I'm just going to add 100,000 to that. So it's 604,950.5. Okay, so we're right down to basically what we were before. We're going to take our 10 volts and we're going to divide it by the 604,950.5. So 10 divided by 10 divided by 604,950.5 gives us 16.5 milliamps, or microamps, I'm sorry. Microamps. So you can see we got about twice as much current flowing through there now. But we need to find out what the voltage drop is going to be right here. Since we have this in the circuit now, it is now part of the circuit. So we can find the voltage drop. This is really the easiest way to do this, is we can either do one of two things. We can either find the voltage drop here in this circuit with this current running through it, and then subtract that from 10, and it'll give us the current flowing, or the voltage across these resistors. Because remember, the current's going to be the same through each one of these. But now this is in the circuit as well. So the easiest way to do this is either to, like I said, either find the voltage drop here and subtract it from 10, or find the voltage drop across this parallel combination of resistors, and that'll give us our voltage drop. So right here is our effective parallel resistance right there. So we'll just go ahead and do it from that, and we're going to go back to E equals IR. We know the current because the current through the combined two is going to be the same through the whole circuit as the total current through there. So, and I'm going to actually do this both ways. So I'm going to take the 0.0000165, that's my current, and I'm going to multiply it by this resistance, which is 504,950.5, equals 8.332 volts across this point to this point. Let's double check this. Let's take our current, 0.1000165, and let's multiply that by this one right here. Let's get the voltage drop across that one. So 100,000 gives us 1.65 volts. Now, Kirchhoff's law again. Since we combined these two and found the effective total resistance between these two that are in series with this one, the voltage drop across this one plus the voltage drop across this parallel circuit should be equal to or pretty close to 10. You got to take into account we've had a little bit of rounding going on, so it may not be quite perfect. So I'm going to take the 1.65 that we just got and add 8.332, and we get pretty close, 9.982. Like I said, there's some rounding going on. So with a 1 mega ohm input resistance or impedance on our voltmeter, we're going to have a reading of 8.332 volts approximately from this point to this point. Okay? So, let me pause here a second again. I'm going to get the circuit over here and let's take a look at that. Let's actually see if that's pretty close and see what it does. Okay, and I've got the circuit on the trying to find the best lighting here. I got the circuit set here. We're going to take a look at this. If you can, let me see if I can get this in the right spot here, and we can tell. So I have a resistor that's right here. This one right here. That's our 100k ohm. Here I have 4 100k ohm and about a 620k in series right here. So these are making our 1.02 meg ohm, where this is our 100k resistor right there. So that's our circuit. I do have positive and negative hooked up here. Let me see if I can get the lighting a little bit better here. It's almost too dark, but it's almost too bright. So let me get this down here where maybe we can get to actually see what's going on with it. Trying to get the glare off of it. I might just have to lose that light. Okay, I think y'all can read that right there. So first off, just to show, I have power supply leads here. I'm going to hook this up and we're going to take a look at the voltage coming straight out of the power supply. I have just a variable power supply sitting over here that we're going to take a look at, and we're going to set it and make sure it's at 10 volts. So it's a little bit low, coming up just a touch. I'm adjusting it right there. So we're at 10 volts right now. So just to show that we have that as our supply, now I'm going to hook it up to our circuit. Alright, and then we're going to test our voltages and see if we can compare them to what we had right here. Now remember, originally this is supposed to be 9.1 volts. We're figuring it's going to measure at 8.332 volts across this point and 1.65 volts across that 100k resistor. So let's go ahead and check the 100k resistor. I'm just going to go on each side of it and find the voltage drop. Hoping y'all can see that. Okay, so this is voltage drop across this resistor, which is actually showing a little bit different than what we were thinking. Okay, well, maybe some things are changed. Let me test it to this point. Well, there's is our 8.33 volts, pretty close. I'm wondering if I got some resistance in my... So that's showing 0.8 volts. Which could have something to do as well. Actually, we also have to take into account that I'm adding this into the circuit a little bit differently than we figured in our math, because I'm putting this as part of the circuit in a different spot now. That is true the 1.6 volts would be true if we had figured it over there with the 1 meg ohm as well. So that could be our discrepancy right there. But between the 2 points that we had indicated on our schematic, we do get approximately 8.35 volts. Now, let's go back, and I'm going to hook up the VTVM to this just a moment. I need to move the camera around just a little bit, and let's get a comparison of the two voltages. And then we'll run the math on the 10K, or the 10 meg ohm resistance. So give me just a moment. Let me get my camera set back up for that, and we'll... Alright, so we're back. Up there in the corner you can see the VTVM reading, and we'll see what the reading shows according to where we had our 1 meg ohm input voltmeter in parallel with that run resistor, and so we're going to test at the same point. So as you can see right there, I'm trying to read this. Let me go to big reading. Right at 9 volts. Sorry, that's a little out of focus. I got to improve that camera. It's not an auto focusing, and I might not have got it focused just right. But as you can see, it actually shows right at about 9 volts, which is also very close to where we figured it should be as a standalone circuit. If you remember, right here, 9.1 volts. .1 volts, and as you, I'll let you see that I am testing it right there at the same point, and it's actually just a touch over 9 volts. So you can see this is actually giving us a closer reading to what it was supposed to be in that circuit. Let's find out why. So give me just a moment. Let me get the dry erase back up here, and we will go through the math. Alright, so we're back here with our whiteboard, and I'm going to go ahead and remove some of this. But before I do, I am going to write down this voltage right here. This 8.332 volts. That is what we had with the 1 meg ohm meter. But now, instead of having a 1 meg ohm meter here, we have an 11 ohm meg ohm, 11 meg ohm meter in line here. Remember, we tested that earlier, and it was showing coming out right about 11 meg ohms. So we've already determined this still stays 100K, but let's figure this out right here now. So we're going to have R1 times R2, R1 times R2, which is 1,020,000. And I'm just going to put times 11 million ohms. Get my trusty calculator wherever I happen to put it. Ah, there it is. And do the same thing. So 1,020,000 times 11 million, and then we're going to add these together. So 11, oops, 11 million plus 1,020 1,020,000 gives us 12,020,000. So we're going to divide that original number by that. Gives us now 933,444, and I'm going to call it 0.26 ohms. So it's considerably higher now. A lot higher resistance right there. So let's do this the same way we did it before. We've now found the combined total resistance of this parallel circuit here. We're going to go ahead and add 100,000 to it, which is going to give us 1,033,444.26. We're going to put that back into this one right here and find our total current that's running through this circuit now. So we're going to take our total voltage, which is 10 volts, and we're going to divide it by this. So 10 divided by 1,033,444, and I hit the wrong button there, so 10 divided by 1,033,444.26 gives us 0.000096, and I'm going to call it 8. Just rounding up that third digit there. And that's amps, or 9.6 microamps. So as you can see here, before we were like 16 microamps for our total circuit, which means we're increasing the amount of amperage being pulled through here by nearly half of what we were with our 1 meg ohm VOM, which means literally we're loading the circuit less. So we've got our current, and we've got to have current running through this right here. It'd be splitting it, and of course this resistor obviously would have a slightly different resistance or current running through it than this one, but it's still effectively the same one. The voltage is going to be the same. So we're going to take our E equals IR, and we're going to take this number right there, the 9.6 microamps, 9.68 microamps, and we're going to multiply that by our resistance of right here, which is the 933,000. 444.26 equals 9.03 volts. See how we have such a difference here? And this really, this isn't as bad as it could be. For one, we had a 1 meg ohm VOM. And as you can see, when we did measure it, it came out to just about, it was just a needle's width past, maybe, the 9, when we measured it with the higher impedance, 11 meg ohm resistance, input resistance. But we've got 0.7 volts here. And that's only about a 1.1 meg ohm circuit we got here, and we're just measuring across a 1.02 meg ohm point here in that circuit with a 1 meg ohm VOM, this one right here. Imagine if this had been an analog one, and we're measuring 10 volts. So say it was in the 20 volt range, and it was a 10,000 volts or 10,000 ohms per volt meter. Well, that's only 200,000 ohms. That's even lower than the 1 meg ohm that we had on that one, which would have made this effective resistance right here even lower. Because remember, if you got two resistors in parallel, the total resistance between the two is going to be less than the smallest one. As you can see here, we got 933,000 and some change ohms, which is less than the 1.02 meg ohm, which is the smaller resistor in this parallel circuit right now. When we were at the 1 meg ohm and the 1.02 meg ohm, which still stayed the same, it was only, 504,000 ohms, which was definitely smaller than that. In fact, it was nearly half. So the current is increased in the circuit, which loads it. It's got more current running through it. The effective voltage drop across here is less because there's not as much resistance in this between these two, which is going to increase the current through there to some degree. It's nearly twice through the circuit. So you could see having an even lower voltage or lower resistance between these two, because we have an even lower impedance VOM, is going to load that circuit down even further. This isn't too much off of that. That's 0.07 volts. I mean, you can get that much error out of trying to decide if you're looking at your needle straight on. Or maybe you just barely had it out of calibration. You didn't have it zeroed quite right. This, if you're reading the schematic and it said, or the service manual, and it said to use a 10 meg ohm VOM, which at least 10 meg ohm VOM, which this VTVM at DC readings is 11 meg ohms. In AC, it's still 10 meg ohms. And it doesn't matter what voltage range I'm on. It's that impedance. Period. This one, and like most digital ones, it doesn't matter, like I mentioned before, on the old analog ones, it depended on which range you were in. And then you had your ohms per volt rating for the whole meter. So if it was 10,000 ohms per volt and you were on the, say, 200K on this one. Oh, I'm sorry. The 2,000 millivolts, which is 2 volts. Now you only have a effective resistance of, 20,000 ohms? Imagine putting that into this equation. Or you go up to the 20 ohm one at 10,000 ohms per volt. Now we're at 200,000. We're still way down. I mean, even this one right here is still 5 times in the same range than what an analog one would be. And they vary. Some of the older meters were even worse than the ones that you can buy now that are still analog. But you got to check that. If the service manual says check this with a certain volts per ohm, or it needs to be at least a 10 meg ohm voltmeter or an 11 meg ohm voltmeter if it's on DC. Most VTVMs are 10 meg ohm, and then the DC is 11 meg ohms because it's got that 1 meg ohm resistor that's actually in series with it, typically in the handle. So you can see just in this circuit right here, actually I'm sorry, that's 0.7 volts right there. Wow, I still wrote it wrong. 0.7 volts. roughly. That if you were reading that and you were doing, reading the manual and it said 9 volts, because if they used a 11 megohm VTVM to measure it, they probably would have said 9 volts. Well, you're looking at 8.332. You're probably going to make an adjustment to this circuit to bring your reading with your 1 meg ohm meter up to 9 volts. You take the meter out of there, now it's over 9 volts. Because once you've taken the meter out, you've unloaded the circuit and the voltage goes up. Because you're not drawing it down any with the extra amperage. So just be cautious about when you're reading through a service manual or something, to realize that this might not be right. But it's really easy to check what it is. If you got another ohms meter that has at least 2 megohms. This one's 2000 K, which is 2 megohms, is the highest reading that you can read ohms with. If you got another one, just put the other one in ohms, put this one in volts, and measure the resistance. If it comes out to 1 megohm, you have a 1 megohm DMM. Some of them are 10 megohm. Usually some of the higher priced ones, probably some flukes out there. But you need to check that. Find out, and it may be in the specifications. But it's definitely important to make sure you're using the right VOM. And if it is an older piece of equipment and it says to use a 50,000 ohms per volt meter, well, just find out, okay, so like on this right here, say it had a 10 volt range. We could measure that in a 10 volt range. So I said 50,000. So now 500,000 ohms is what that meter is going to have in that voltage range that you select. Well, 1 megohm is even higher than that. So you're probably not going to have exactly the same reading, but it's going to load the circuit down less. You'll probably show a higher voltage than in what their service manual says. But you might just have to kind of do the math. Find out if that's the case, can I use the 1 megohm? But that's probably going to be a very, very old piece of equipment that you're working on. Most of them are going to say that you got to have something with a 10 megohm input resistance, which a VTVM is going to have. A lot of these can. This is just a $10, $15 maybe digital multimeter, and it works for most things. And a lot of newer stuff is going to have lower impedance circuits in them. This isn't even as high an impedance circuit as you could possibly see in some tube stuff. You could maybe have something that's 2 or 3 megohm here. Well, that's definitely not going to work with this, because now we even have an input resistance that's less than the impedance of the original circuit, which is definitely going to drag it down. So just remember that. Most modern equipment, you're probably not going to run into that problem quite as much. I guess you could say just kind of a halfway rule of thumb. I don't even know if I want to call it a rule of thumb. High voltage circuits, old tube radios, stuff like that, typically had a higher impedance circuits in them. Low voltage, 13.8 volts, 5 volts, 9 volt circuits are typically lower impedance. So these work great for lower impedance circuits. They're not going to load it down much. Tube radios, some of the high voltage and high impedance circuits, this could drag it down and give you an erroneous reading. And in this case, if I was using this one and I knew enough of the circuit to do the math, I would know that that's a good reading. even though it says 9 volts, I would know that's a good reading. But unless you want to do the math on every test point, you might be just able to find a DMM that's got at least a 10 megohm input resistance. So I'm hoping this didn't confuse too much, especially when I'm going through and making a few mathematical errors along the way, not getting enough zeros in things and whatnot. But it's pretty late at night, so I hope that maybe kind of explained the little things. And not all voltmeters are created equal. And I hope you kind of learned something from this. Like I said, a little bit different video than normal. Not working on something, just kind of wanted to go over this. So thanks for watching. Hopefully you hung out through the whole thing. Probably came out a lot longer than I was planning. But I like to make my videos just kind of straight through. Maybe do a pause, but not really a lot of editing. That way you kind of see everything that goes through the whole video, besides maybe some camera changes. So thanks for stopping by, and we'll see you next time. Bye for now.